Okay, in this chapter we're going to look at nomenclature. Now, in introductory chemistry, that covers all of the periodic table, but it is kind of somewhat limited compared to other things. It's not like we're going to be doing nomenclature of our big complex organic molecules like acetylsalicylic acid, which is aspirin. We're actually limiting it to uh, smaller molecules. A lot of cases, it's just flat out binary compounds or even less. What I mean by a binary compound, it's going to be made out of just two elements. It could be any two elements on the periodic table that are combined, but that's typically what we're going to focus on. Now, the reason we're only doing that is when you get to the three compounds or more, it gets more complex. Like, for instance, there's a whole family of compounds that have the relationship of for every one carbon, there's two hydrogens and one oxygen. But that family that has that ratio of one carbon to one water molecule, they're all carbohydrates. And not all carbohydrates are the same because technically vinegar is a carbohydrate and glucose is a carbohydrate. So the nomenclature will expand as we get into more chemistry. And it does get quite complex. But we're going to keep it simple right now by comparison with the binaries. Now, I'm not trying to say this is the simplest stuff in the world. It's not, but it is simpler than it gets much later on. So that's why we do chemistry, we build up to it. That's why this first couple years of chemistry, we still call them general chemistry. All right, so let's focus on these and let's start explaining what's going on here. Now, technically, your book breaks it into four different categories. Type 1 and Type 2 um, names are with more of what we call ionic compounds. You're going to see most of these are from the periodic table. You have a metal and a non-metal. The exception is in place of some of the metals, we have NH4. That's what it's talking about on this right here. NH4 also behaves like a metal ion. So this is metals or NH4 positive, and then a non-metal. And then type 2 are just two nonmetals. Now, type 2, type 3 are just two nonmetals. We're going to find those are typically easier to name, especially when they're binary, because even like NH3 or H2O, we really can just use little prefixes to say what they are. We'll see those in just a bit. And then our type 4 are acids. And we're going to see there's just two really different name rules for acids. There's only two different classes of acids. So most of our work here is going to be spent on type 1 and type 2 because those are the more complex of our nomenclature. Ionic compounds in general are harder to do than the molecular compounds. All right, so let's work on type 1. Now, the first type of ionic compounds are much easier to name than type 2 ones, but type 1, there's a limited number of metals that fit into type 1. Now, what I mean by limited number, it says down here, group 1, 2, aluminum, zinc, cadmium, and silver. So what that means is, here on the periodic table, everything in group 1 and everything in group 2 are part of that type 1 atom. Now, what that means and reason they are is everything in group 1 likes to form positive 1 ions, everything in group 2 likes to form positive 2 ions, and there's no other choices. So anytime you see sodium in like a compound like this, you know that that sodium is going to be an Na plus when it forms an ion, because all sodiums do that. Everything in group 1 makes a positive 1. Everything in group 2 is positive 2. Now, these other guys aren't necessarily singled out by their groups, but their charges are fixed. So every single aluminum you ever see is a positive 3, every single zinc is a positive 2, every single cadmium is a positive 2, and every single silver is a positive 1. All right, so when we see a name for a chemical, and not the formula, the actual name, that metal, any one of these, is just going to be listed first. So if I put aluminum with anything, my name is going to be aluminum. And then we'll have our nonmetal there. Now, the weird thing is on the nonmetal, that is just the name of the nonmetal typically with the IDE suffix. So if I wanted to put aluminum with chlorine, I would have aluminum chloride. Just like this sodium chloride, that does mean there's a Cl there. Now, along with this positive charge, it turns out the nonmetal is also going to have a charge. And we can kind of do it similar to what we did on the metals. It's like we said, group 1s are always positive 1 and group 2s are always positive 2. Well, on the other side, that first group coming back, group 17 is negative 1. So fluorine, chlorine, bromine, iodine like to be negative 1. Oxygen, sulfur, and selenium like to be negative 2. Nitrogen and phosphate are negative 3. So it just goes back 1, 2, 3. So since this is chlorine, that's going to be a negative 1. And if I did a similar thing with the aluminum chloride I did up here, the aluminum is positive 3 because it says so, and the chlorine is negative 1. Now the neat thing is, once you get these charges all figured out, to figure out the actual formula, we just actually combine them so the charges cancel out. What I mean by that, you have 3 positive charges here with the aluminum, but only 1 negative. To cancel them out, aluminum chlorine needs more chlorides. 3 chlorines, because that would give you 3 negatives. I didn't have to do that with sodium chloride. Since that's a positive 1 and that's a negative 1, this is just NaCl. We always combine those positives and negatives so they cancel out. Well, that actually makes getting the formula a little bit more tricky. But if I give you the formula and I just ask for you the name, you don't have to do any of that. So K(Ni) is just potassium. That's an O. Potassium, because that's the metal. Iodide, because iodine gets turned into iodide because it's part of an ionic compound. Magnesium and bromine. Magnesium, bromide. Barium and oxygen. Barium oxide. The only reason we ever need these charges is if we need to get those formulas. We have to get those ratios of our metals to our nonmetals. Now, when you sit down and practice these typically come relatively easy with a little bit of practice, the type 1s do. Type 2s, the next ones, are slightly harder, and that's because it deals with all those other metals. So we said on the periodic table, we figured out how to do group 1 and group 2, and then just aluminum, zinc, cadmium, and silver. But we skipped all these others. So iron, even though we all know iron's part of steel and there's a lot of iron out in the world, we didn't talk at all about that and how we name it. Well, the reason we skipped items like iron and all these other guys is because they don't have just one charge state. Iron, for instance, can be more than one. So what we would see on something like iron, we would actually see the word iron and then in parentheses a Roman numeral. And then the anion. And it might be a different number. It doesn't have to always be 2. There's also iron with the number 3 there. And it might also be with oxides. Matter of fact, iron ore, the raw rock that we get iron out of, you have iron 2 oxides and iron 3 oxides mixed in. Matter of fact, they're both rust colored. They look almost identical. All right, but their formulas are going to be different because this Roman numeral, that tells you the charge of the iron. So iron 2 has an Fe2+. Iron 3 is Fe3+. So that Roman numeral is telling you the charge. Now the oxygen we still get from the periodic table. It still fits the same category before. So since it was 2 from that end, it's a -2 species. So this is an O2- and this is an O2-. Does mean that iron 2 oxide, since it's a 2 and 2, is just FeO. This one takes a little bit more work because I need to get this up to a +6 and this to a -6. So it's Fe2O3. We have to do a little bit more work, but those Roman numerals are beneficial. Now, we have to go backwards, is what we're going to do down here. We have to figure out the Roman numeral for the metals on each of those. So how we're going to do that, we're actually going to figure out what the negative ion is charged. So chlorines are in that second to last group on the periodic table. So they are -1s. So that one's a -1, and this is a -1. And I'll go ahead and mention that the sulfur is -2. It's right underneath oxygen on the periodic table. All right, so if this is -1, this iron, because there's two of these, would have to be a +2. So that first species is iron 2 chloride. The next one, since there's now 3 chlorines, is going to be iron 3 chloride. Now, it's just a coincidence that that number turns into this. Doesn't always happen that way. All right. Now, I got 3 of these -2s. So that'd be a total of -6. And I want these 2 golds to add up to +6 and neutralize that out. So these are both +3s. So we have gold 3 sulfide. Now, you're going to be given that charge for the metal somehow. It's not like you're expected to know that iron can be 2 and 3. So I would have to give you that formula of Fe2 or FeCl2 or FeCl3 or the actual name with those Roman numerals. So that's how you're going to get that charge, is I have to somehow give it to you. I'm not expecting you to know what charge states are possible. But all of those that don't fit into type 1 metals can have variable charges, and they do change quite a bit. Okay, along with those, this is that same stuff we just talked about with those. So along with those type 1 and type 2, we will sometimes change the anion. Instead of just being a single element like chlorine or oxygen, it might be what we call a polyatomic ion. Now, a polyatomic ion, a lot of them do have oxygens with them. Like that chlorine, it might be a ClO- or ClO2-. That's a minus. It looks almost like a 2. Or there's a ClO3- and there's a ClO4-. Now, these are all related to each other, but those other oxygens stay on that chlorine and create a very specific ion. It behaves just like a chlorine ion. It'll just stay with those oxygens around it. Matter of fact, this one right here, we all are aware of what bleach is. That top one is hypochlorite, which is part of the active ingredient or the disinfectant part of bleach, which is sodium hypochlorite. So these do come around, and you do come in contact with these. But these polyatomic ions just change how we go about naming them. Matter of fact, so we just saw on that very first page, NaCl is actually sodium chloride. Well, I just told you that this was hypochlorite. So it turns out NaClO is, that should be sodium. Sodium hypochlorite. And we don't change the suffix. If it's one of these polyatomic ions, we just say the polyatomic ion. So in your book, it's I think it still is table 5.4. It is a table that looks like this. Has a bunch of polyatomic ions in it. And it's just got their names is what they are. And all of them are negative except for ammonium. Ammonium is the only one that's NH4. I do give you some on the periodic table I provide you. So on the back side of it, on this piece of paper version of it, it'll be the second page on your test and practice test. It has some of them right up there. Now, it is to your advantage to have these memorized because it can save you some time, but there's really no reason you couldn't have this sitting right next to you while you take the test. And some people do that. And it can be something kind of like a crutch. I wouldn't want to be totally dependent on it. You want to be comfortable enough that most of these are ones you remember. And you do see that some of these are far more common. Um, Nitrates, for instance, and sulfates are ones that we find biologically, phosphates as well, and acetates. So some of these you see more often just because they pop up some, and you might get more comfortable knowing those. But try to get some practice with them so you know them, and more importantly, be aware where they're at so you can regenerate that information if you need to. And this is a weird thing. This is back when I made my students actually keep it all memorized. This was something to help us learn it, but we don't need to worry about Nick. All right, so which of these is a nitrite? All we'd have to do is go back to something like that table we just saw, and we know that nitrites are just NO2 minuses. The top one is nitrate with an ATE. You notice how there's just a single O difference? You'll see that's the difference between all ATEs and ITEs. There is just one oxygen different. Now, this doesn't actually exist, and that doesn't actually exist, not as a polyatomic ion that you will see, but this one does. It's actually just called nitride because it's a nitrogen all by itself. All right, that in combination with those variable charge states of the metals is why type 1 and type 2 nomenclature rules are more intense than type 3. Type 3 are by far the easiest ones to name because they have a very defined set of rules. So all of our type 3s are binary molecules that are made of two non-metals. So on your periodic table, two of these guys. Now, most of these, you can already tell me what they are because we see them all the time. Like, what do we call a carbon with two oxygens? As in CO2. Yeah, we call it carbon dioxide. That di is a prefix in front of it. So that would actually apply here as well. That SO2 is actually sulfur. You name the metal, the first one just what it is. Second one, we're going to change to IDE, just like we did with the ionic compounds, but we're going to put a di in front of it because there's two oxygens. So that is sulfur dioxide. Now, what do you think prefix you might use in front of a 5 for this PCl5? Yeah, it's going to be phosphorus pentachloride. You will sometimes, when there's just one, see mono, so monophosphorus pentachloride. But the biggest time we use mono is if we want to draw attention to it. Like this guy, CO2 gas, carbon monoxide. We typically stress that because we all know what carbon dioxide is. That's just what we exhale to lose some of our carbon buildup. Carbon monoxide is a poisonous gas that happens when cars don't fully burn their gas. So there is a drastic difference. And that's why most of the time we don't use mono. All right, this one, dinitrogen pentaoxide. Dinitrogen pentaoxide. And on this next page, I have those prefixes. But most of you are going to look at these and say, well, yeah, these make sense. I do imagine some of you might have said quad, because that's a little bit more common for 4, but tetra is the one that we use. Kind of like, you remember that game Tetris? Might be giving away my age to say that was that. But Tetris was just a combination of 4 blocks, and you drop them down and stack them up. Tetris came from tetra. All right, type 4 is naming acids. We're going to find there's really only 2 types of acids we name. We actually name binary acids, which is where we're going to take a single element that's a non-metal and put it with an H. So HCl, H2S, HBr, HI, HF are binary acids. All the other acids we're going to see, a third element that's going to be in there is oxygen, and they're all going to be derivatives of some of our polyatomic ions. So what I mean by that, SO4 is one of our polyatomic ions, we just put an H with it. NO3 is one of our polyatomic ions, we just put an H with it. Now, the binary ones and the oxo acids have two different set of naming rules. All right, what I mean by that, if it is just one of these binaries, like HCl, if it's a gas, we call it just hydrogen chloride. Kind of follow the rules like an ionic compound. Hydrogen sulfide, hydrogen chloride, if it's a gas. If it's dissolved in water, though, it becomes an acid. And instead of saying hydrogen, we say hydro. And we're going to bring the chlorine right next to it. So it's all one word, hydrochlor. But instead of IDE, we put an ic and then a space, acid. So hydrochloric acid. This guy, H2S, as a solution, becomes hydrosulfuric space acid. So anytime it ends with just IDE, you do that. You put hydro in front of it, you put an ic acid there. Change that hydrogen to hydro, IDE becomes ic acid. All right, now, if it's polyatomic ion, so that's sulfate, that's nitrate. We're not going to use the hydro part at all. It goes away. So the sulfate, which is SO4, 2 minus, if I put that with H's, it becomes sulfuric acid. No hydro. Sulfuric acid is just putting H's with the sulfate. Now, if it's sulfite, which is SO3, 2 minus, that becomes sulfurous acid, which is H2SO3. So on your oxos, find that suffix. If it ends in ATE, you change it to ic acid. If it ends in ITE, it's OUS acid. So let's see if we can figure out what HNO3 is. So what do you know about NO3? When in doubt, go back and look at those polyatomic ions, and you'll see that that is nitrate. And since it ends with ATE, HNO3 is nitric acid, sorry. Nitric acid. Practice those. With practicing all these, the only ones I expect you'd have a lot of difficulty time are those type 1 and type 2s. The acids seem to be confusing, especially how this is set up, but by practicing them and practicing separately your binary acids and then the oxo acids is beneficial. Unfortunately, on the little worksheets I gave you, I did keep them separated, so build up those practice skills. All right, there's our summary for those two, and that's some examples. So let's practice these, and then we'll be done with it. So ClO2, to figure out what this, how to name it, we'd have to actually know what that polyatomic ion is. And ClO2 happens to be, and I'll put that up here, ClO2 minus is chlorite. And since it is with just an H, HClO becomes chlorous acid. All right, next one, CO3. Our polyatomic ion list would tell us that that is carbonate, ATE. So its acid is carbonic acid. Ironically, we used to see this in sodas all the time, carbonic acid. Technically it's still there, but acids are a bad, scary word. Turns out this is what you get if you dissolve carbon dioxide in water. So carbonated water is actually the new name of carbonic acid. All right, our next one, H3PO4. PO4 3 minus is phosphate. So we're going to change our ATE to ic acid. Phosphoric. You actually also see phosphoric acid, mainly because it sounds a little bit better than phosphoric. And then our last one here, C2H3O2. If we look on that polyatomic ion sheet, you'll see that that is acetate. So that becomes acetic acid, which is vinegar. All right, now going the opposite way. I give you hypochlorous acid. Since it's OUS, we know that is hypochlorite, which is on our table. It is ClO minus. To make the formula for its acid, we're going to put one H for every single negative. So hypochlorous acid is HClO. And there should be more space here, but perchloric acid is something different. Perchloric acid comes from perchlorate, which is related to hypochlorite, just has more oxygens in it. It actually has 4 oxygens. Still single negative, so we only add one H. So perchloric acid is HClO4. All right, that finishes us up with this chapter. Hopefully we have enough practice items on it. If you need more practice, ask me for some more questions and such, and I can give them to you. Or check your book. Your book has got to have a great amount of resources.